In all of our previous examples, we considered annual compounding, which means that interest is earned once a year. Now, what happens if interest is earned, say, semi-annually, or quarterly, or monthly? In this video, I'll show you what changes when interest compounds on a shorter time horizon. So consider this example. On the top, we have $100 in year 0 that's compounding once a year at 10% for 3 years. Now, at the end of 3 years, we can calculate the future value of $100 using our compounding formula. So the future value equals $100, which is the present value, times 1 plus the interest rate, which is 1.1, raised to the third power. And that gives us $133.10. Now, what happens if this $100 is compounding semi-annually? So instead of compounding 3 times over 3 years, it's compounding 6 times over 3 years. Well, instead of doing it at 10% a year, we can think of it as compounding semi-annually at 5%. And so what we can do is calculate the future value in this scenario. We know that the future value equals the present value, which is 100, times 1 plus the interest rate, which is now 1.05, raised to the 6th power because we have 6 periods of compounding. And that gives us $134.01. So, as you can see, the future value in 3 years is different under annual compounding and semi-annual compounding. There's a few things I want you to take away. And the first is that when the time horizon is shorter for compounding, we are earning interest on top of our interest. And that's what's happening in the semi-annual example here. As a result, because we're earning interest on top of our interest that we've already earned, the future value will be larger under semi-annual compounding. As you can see, $134 is bigger than $133. Because the future value is larger under semi-annual compounding, it also means that the present value is smaller under semi-annual compounding. And a quick and dirty way of thinking about this is we know that under semi-annual compounding, $134 in the future is equivalent to $100 in the present. Now, if the future value was, say, $133.10, then the present value should be equivalent to something a little less than $100, making the present value smaller under semi-annual compounding. Another way to think about it is the fact that when we're moving from the future to the present, we're discounting. And instead of earning interest on top of our interest, we're discounting off of our discount. And so as a result, we're going to get a smaller present value with shorter time horizon discounting. All right, so we can calculate something called the effective annual rate, also known as EAR or EAR. And what that's defined as is the annual rate which causes the present value to grow to the same future value as under intra-year compounding. So applying that to the example we just looked at, the question would be, what is the EAR for a 5% semi-annual compounding, which was essentially the bottom time graph of this previous slide, so this one right here. All right, well, if we invest $1 now, in 1 year, that $1 would compound twice at 5%, so the future value in 1 year is just 1 times 1.05 squared, and that equals 1.1025. And so the effective annual rate is 10.25%. It's whatever is on the right-hand side after the decimal point. And it's 10.25% because that's the rate that produces the same future value after 1 year under annual compounding. So 1 times 1.05 squared equals 1 times 1.1025. Another way to say it is compounding semi-annually at 5% is equivalent to compounding annually at 10.25%. Now there's a formula for EAR, and that's given by the box here. It's EAR equals 1 plus the stated interest rate divided by M, M is the number of times that the interest compounds within a year. I is the interest rate for that compounding. And that value is raised to the nth power minus 1. So, for example, under EAR, M equals, under an annual EAR, M equals 1, right? So you use the formula, and what it tells you is that 1 plus the interest rate raised to the first power, which is just 1 plus the interest rate, minus 1 will give you the EAR for the annual rate. Well, 1 plus I minus 1 is just I, so it's just 10%. So that makes sense. Now, if our money is compounding quarterly, then it's compounding 4 times a year, so M equals 4. And we can calculate the effective annual rate using this formula. So it's 1 plus 0.1, which is the interest rate, divided by 4, raised to the 4th power minus 1. And we find that the effective annual rate at a quarterly compounding level is 10.38%. So again, what this means is that if a dollar were to compound 4 times, then at an annual interest rate of 10%, then the effective annual rate is actually equal to 10.38%. We can do this for any number of time periods. So, for example, if we have daily compounding, then that's equivalent to an annual compounding rate of 10.52%. So you can see that as the frequency of compounding increases within a year, the effective annual rate is also increasing.